Welcome back to ME515 Finite Element Methods in Engineering. Is Dr. Jitendra Prasad. Today we are going to solve textbook problem 8.2. Figure is as shown and the problem statement is as given here. It says consider a triangular panel made of two isotropic materials with thermal conductivities of K1 equal to 4 watts per degree Celsius and K2 equal to 8 watts per degree Celsius as shown in the figure above. A constant temperature of T equal to 10 degrees Celsius is prescribed along the edge BC. The edge AB is insulated and a linear distribution of flux Qn equal to 15x watts per meter is applied along the edge AC. Point source P equal to 45 watts is applied at x equal to 3, y equal to 0. Plate dimensions are in meters. For the finite element mesh, consider two triangular elements ABD and BDC. Carry out calculations manually and find the temperature and flux distributions in the plate. Now solution. Let's look at the steps that we have to follow in order to solve this problem. Step 1. Number the nodes counterclockwise. This is because we want the area to be positive. If we don't follow counterclockwise numbering, it is possible that the area becomes negative for the elements. So here is the division as given in the problem itself. There are two elements. So let's start with number 1 at the leftmost point of the plate given. Number 2 as shown here. Number 3 the rightmost point and number 4 is the topmost point. Step 2. Number the elements. Let's call the left one as element number 1 and right one as element number 2. Step 3. Construct stiffness matrix for element number 1. Step 4. Construct a stiffness matrix for element number 2. Step 5. Assemble global stiffness matrix. Step 6. For element number 1, compute force vector due to prescribed flux. Step 7. For element number 2, compute force vector due to prescribed flux and point source. Step 8. Assemble global force vector. Step 9. Solve for unknown temperature. And step 10. Compute temperature and flux distribution. Okay, so step number 1, that is numbering the nodes, and step number 2, numbering the elements, we are already done with. We are here at a step 3, which is to construct a stiffness matrix for element number 1. In the problem we solved earlier, 8.4, there it was, in the problem itself it was given conductance matrix. So I want to mention here that conductance matrix and stiffness matrix are both same. We already know that a stiffness matrix is equal to K times integral of B transpose B integrated over the whole domain, which turns out to be K times area times B transpose B, where B is as given here 1 over twice the area of the triangle multiplied by a matrix containing y2 minus y3, y3 minus y1, y1 minus y2, and x3 minus x2, x1 minus x3, and x2 minus x1 as members, where A is given by half of determinant of a matrix containing 1 x1 y1, 1 x2 y2, 1 x3 y3, where x and y here are the coordinates of the vertices of the triangular element. And the subscripts here correspond to the local numbering. So if you look at the original global numbering for the first element, the global node number is 1, 2, and 4. However, in local numbering, we have to renumber it. So let's say global number 1 corresponds to local number 1, global 2 still is local 2, and global 4 is now local 3. So from the problem statement, what we have is x1 is 0, y1 is 0, x2 is 2, y2 is 0, x3 is 2, and y3 is 3. And we can calculate the stiffness matrix based on these coordinates. And we know that for element number 1, k equal to 4. So let's calculate the area first. Area, we put the values here in the determinant, values of the coordinates, and what we get is area equal to 3. Then the B matrix, we use the formula as shown here, and the corresponding values we get, final value of B is a matrix containing minus half, half, 0, then 0, minus 1/3, 1/3 as members. So based on the B matrix, we can now calculate the stiffness matrix. As we know, big K equal to a small k times A, B transpose B. We put those values here and we finally get the value of a stiffness matrix K equal to a matrix containing 3 minus 3 0 minus 3 13 over 3 minus 4 over 3 0 minus 4 over 3 4 over 3. Now step number 4, construct a stiffness matrix for element number 2. Now we have two choices. First choice is to construct the stiffness matrix as we did for element number 1, and the second choice is to somehow extrapolate the results we got for element number 1. While first choice is easier, but it may take more time. The second choice is intuitive on the other hand and can be calculated very fast. So I'm going to demonstrate that. This is element number 1, a stiffness matrix for element number 1, and the local numbering is as shown in the figure, while the global numbering is in black, the local numbering is in red. Now for element number 2, there are two things which are different. First thing is the conductivity. So instead of K1 equal to 4, we have K2 equal to 8. And second thing is, this is the second element is a mirror image of the first one. So let's look at it one by one. If the second element were the same as the first element, with only difference that conductivity is twice as large that of element number 1, then the stiffness matrix would be given by Ka equal to K2 over K1 multiplied by the original stiffness matrix for element number 1. So K2 over K1 is equal to 2, hence Ka, that is the stiffness matrix for element which is same as the first element with only difference that K2 is 8 instead of 4, will be 2 times the stiffness matrix for element number 1. Now element number 2, as I said earlier, is a mirror image of element number 1. So if we reflect the first element with respect to a vertical line, then if we don't change the local numbering, that is, if we leave the local numbering same as the earlier, that means the numbering in the second element, the reflected element, is also reflected, then the stiffness matrix for second element would be given by Kb equal to 2 times the stiffness matrix for element number 1. There will not be any change. This is because the numbering has also been reflected. What if now we change the numbering? Because we have to change the local numbers, because if you don't change the original number 1, 2, 3 in the reflected element will be clockwise, which will result in the negative area. So it is conventional that element numbering is anti-clockwise. Hence, instead of clockwise 1, 2, 3 as given in red, if we reorder it 1, 2, 3 as shown in the right figure, which is anti-clockwise, we can get the corresponding stiffness matrix by rearranging rows and columns. And what do we have to change? If we compare the two figures, left and right one, what we see is node 3 remains node 3 and node 1 and 2 are being interchanged. Hence, in the stiffness matrix given on the left side, if we interchange rows 1 and 2 and columns 1 and 2, we will get the stiffness matrix for the element on the right. So if Kb is equal to 2 times a matrix containing 3 minus 3 0 minus 3 13 over 3 minus 4 over 3 0 minus 4 over 3 4 over 3, then the stiffness matrix for the element on the right side will be Kd equal to 2 times a matrix containing 13 over 3 minus 3 minus 4 over 3 minus 3 3 0 minus 4 over 3 0 4 over 3. Now the local numbers are as shown in the figure 1, 2, 3 anti-clockwise, and the corresponding global numbers are as shown in black. So local node numbers 1, 2, 3 correspond to global node numbers 2, 3 and 4 respectively. So finally we know now that a stiffness matrix for element 2 is K2 equal to a matrix containing 26 over 3 minus 6 minus 8 over 3 minus 6 6 0 minus 8 over 3 0 8 over 3. Now step 5, assemble global stiffness matrix. For element number 1 we have K1, we have already calculated that. For element number 1 the global node numbers are also shown. For element number 2 the global node numbers are shown, and corresponding element stiffness matrix is also given here that we have calculated. Now next thing is to assemble them, and for assembling them we will use the data from these two element stiffness matrices. So K will be equal to a matrix containing 3 minus 3 0 0 minus 3 13 over 3 plus 26 over 3 0 minus 6 minus 4 over 3 minus 8 over 3 0 0 minus 6 0 plus 6 0 plus 0 0 minus 4 over 3 minus 8 over 3 0 plus 0 4 over 3 plus 8 over 3. So the final global stiffness matrix is given by a matrix containing 3 minus 3 0 0 minus 3 13 minus 6 minus 4 0 minus 6 6 0 0 minus 4 0 4. Once we have the global stiffness matrix, the next task is to calculate the force vector. So first we will calculate the force vector due to prescribed flux for element number 1. Once we are done with element number 1, we will do the same thing for element number 2. So for element number 1, we have two boundaries. One is a line between node 1 and 2. Let's call it gamma 1 2, and second boundary is gamma 3 1, which is the boundary connecting nodes 1 and 3. In the problem it is mentioned that the boundary connecting nodes 1 and 3 is insulated. That really means Qn equal to 0. So we are writing Qn equal to 0 there. And at gamma 1 2, Qn equal to 15 times x. Now force vector for element number 1 F1 will be equal to minus closed integral of n transpose Qn integrated over boundary gamma 1 2 only. Since Qn equal to 0 at gamma 3 1, the contribution for this boundary will be 0 because Qn equal to 0. Hence F1 will be calculated at gamma 1 2 only. Let us say the values are a vector containing F11, F12 and F13. In order to calculate F1, F11, F12, F13, we are going to use the shape functions n1, n2, n3 at gamma 1 2, and we know that n1 is equal to 1 at node 1, n1 is equal to 0 at node 2, and we also know that between 1 and 2, n1 is a linear. It varies from 1 to 0 linearly. Similarly, n2 is equal to 0 at node 1 and it is equal to 1 at node 2, and it is linear. We have seen in previous video lecture. So n2 varies linearly from 0 to 1, where at gamma 1 2, and n3 equal to 0 at node 1 and n3 is equal to 0 at node 2. So at gamma 1 2, n3 is always 0. Okay, let's say L12 is the distance between nodes 1 and 2, and value is given in the problem. L12 is equal to 2. Then at gamma 1 2, n1 can be given in terms of x, and the expression will be n1 equal to 1 minus x over L12. Similarly, n2 will be equal to x over L12, and n3 will be 0 at gamma 1 2. So F11 will be given by minus integral of n1 times Qn integrated from 0 to L12 with respect to x. And we know that n1 is equal to 1 minus x over 2 and Qn equal to 15x at gamma 1 2, and putting those values here, integrating, we get F12 equal to minus 10. Similarly, F12 we get equal to minus integral of n2 times Qn integrated from x equal to 0 to x equal to L12, that is 2, and the value we get is minus 20. Since Qn equal to 15x but n3 equal to 0, so multiplication is 0, hence F13 becomes equal to 0. So the force vector for element number 1, that is F1, becomes equal to a vector containing minus 10, minus 20, 0. Same thing we have to repeat for element number 2. However, element number 2 has different boundary traction or flux given. So this is element number 2, and we have the local numbering, the corresponding coordinates are also given. Gamma 1 2 as mentioned in the problem, has q1 equal to 15x, then gamma 2 3, which connects nodes 2 and 3, and T is equal to 10 degrees Celsius is given here on this boundary, and there is no boundary at the line connected node 1 and 3. This is because this is connected to the first element. So force vector due to flux F2q is equal to minus closed integral of n transpose times qn integrated over boundary 1 2. Let's assume the final value of this force vector is a vector containing F2 q1, F2 q2 and F2 q3. In order to calculate these force components, we require shape functions, that is n1, n2, n3 at the boundary gamma 1 2. So let's see how the shape functions behave at gamma 1 2. We know n1 is equal to 1 at node 1 and n1 equal to 0 at node 2, and we know that at boundaries n1 is linear, so obviously n1 is a line, n1 is decreasing from 1 to 0 as it moves from node 1 to 2. Similarly, n2 equal to 0 at node 1 and n2 equal to 1 at node 2, hence it linearly increases from 0 to 1 at gamma 1 2. Now we know that n3 equal to 0 at node 1 and n3 equal to 0 at node 2, hence n3 remains 0 throughout gamma 1 2. Again L12 here also it's equal to 2, so expression now will be different than what we saw in element number 1. So n1x will be equal to 1 minus x minus 2 over 2. This is because x, the origin for this element is 2 0. So node 1 is 2 0. Hence n1 is equal to 1 minus x minus 2 over 2, so that when x equal to 2 we have n1 equal to 1, and when x equal to 4 then we have n2 equal to 1. So n2 is x minus 2 over 2 and n3 equal to 0. Conveniently, we can also do some transformation. Let's say xi is equal to x minus 2 over 2, then n1 can be given by n1 equal to 1 over xi and n2 equal to xi and n3 remains 0, where xi equal to x minus 2 over 2 and therefore x equal to 2 plus 2 xi and hence dx equal to 2 d xi. So qn can be also transformed. Now qn as a function of xi can be given as qn equal to 15 times x, that is qn equal to 15 times 2 plus 2 xi equal to 30 times 1 plus xi. Now if 2q1 is equal to minus integral of n1 times q1 integrated from x equal to 2 to x over x equal to 4, where n1 equal to 1 minus x minus 2 over 2 and q1 equal to 15x. Now transforming this integration into xi, and what we get is f2q1 equal to minus integral of 1 minus xi times 30 times 1 plus xi times 2 d xi with limits from 0 to 1, and the corresponding value of f2q1 we get is minus 40. Now f2q2 can be also calculated. So here we have integration of n2 times qn. The value which is calculated after transforming x into xi is minus 50, and q2, q3 will be equal to 0. This is because again qn, although qn equal to 15x, n3 equal to 0, and hence f2 q3 equal to 0. So what we get is f2q equal to a vector containing minus 40, minus 50 and 0. Now we also have to calculate the fourth vector due to the point source, and it is given in the problem that is a point source p equal to 45 is given at the coordinate 3, 0 as shown in the figure as a small circle in red. We know that a force vector due to any source is given by integral of n transpose times s integrated over the whole domain, where s is the source. It's like a body force. Now, if we somehow express P, that is the point source, as a body source S, we will be able to calculate that. Let us say the final value what we get because of the point source is a vector containing f2 s1, f2 s2 and f2 s3 as members. Then in order to calculate that, first we have to define S in terms of P. So S can be given as Sxy equal to P times delta x minus 3 multiplied by delta y, where delta is a direct delta function. That really means if delta x is a direct delta function, then delta 0 or delta at x equal to 0 will equal to 1. Otherwise, delta will be 0 at x not equal to 0. Hence, we can integrate now. So, f2s vector is given by n transpose, which means a vector containing n1, n2, n3 multiplied by s d omega, and this is integrated over the whole domain. Note that n1, n2, n3 here are functions of both x and y, and s equal to now p times delta x minus 3, and delta is a function of y. So delta x minus 3 will be equal to 1 at x equal to 3, and delta y equal to 1 only when y equal to 0, That means the whole expression, the n vector multiplied by p delta function of x minus 3 times delta function of y will be non-zero when x is equal to 3 and y equal to 0. Hence, the integral can be given by p times a vector containing n1 computed at 0.30, n2 calculated at 0.30, and n3 calculated at 0.30. Hence, F2S is equal to P times 0.5, 0.5, and 0 as a member of the vector. That is, F2S equal to 45 times a vector containing 0.5, 0.5, and 0, and final value of this vector is a vector containing 22.5, 22.5, and 0 as members. Now, at gamma 23, temperature is prescribed and temperature equal to 10. Since temperature is prescribed, we don't know what is the flux at this boundary. And because of that, if let us say Qn is unknown, and because of this Qn, there will be a contribution to the force vector. So F2R, if this is the vector due to the force vector due to this unknown Qn, then F2R will be equal to minus closed integral of n transpose times Qn integrated over whole boundary gamma 23. Since Qn is not known, we will assume F2R to be equal to a vector containing 0, R3, R4. The first entry is 0. This is because N1 will be 0 at gamma 23, because gamma 23 is a line between node 2 and node 3, and the first shape function, that is N1, is 0 at both nodes 2 and 3. So total force vector for element number 2 will be given by F2 equal to F2Q plus F2S plus F2R, and we add them together, that we have calculated already, and we get a vector containing minus 17.5, minus 27.5 plus R3 and R4 as members. Now step 8, assemble global force vector. We have element force vector for element number 1, which is F1 equal to F vector containing minus 10, minus 20, 0, and F2 is a vector containing minus 17.5, minus 27.5 plus R3 and R4. This we got for element number 2. From these two element force vectors, we will assemble the global force vector, and for doing that we have to know which all degrees of freedom F1 correspond to, and similarly for F2. So we see that F1 corresponds to global node numbers 1, 2, and 4, while F2 corresponds to global node numbers 2, 3, and 4. So global force vector will be given by big F is equal to a vector containing minus 10, minus 20, minus 17.5, minus 27.5 plus R3, 0 plus R4, which is equal to a vector having minus 10, minus 37.5, minus 27.5 plus R3 and R4 as members. And these four members correspond to nodes 1, 2, 3 and 4 respectively. Step 9, solve for unknown temperature. We know that the final equation is k theta equal to F, where k is the stiffness matrix we have calculated already. Theta is the temperature vector containing the nodal temperatures T1, T2, T3, and T4. We have T3 and T4 equal to 10 degrees Celsius. T1, T2 are unknown. F we have calculated, which is given here. Now, the equation k theta equal to F looks like this one. Here, there are four unknowns, T1 and T2 are unknown on the left side, while R3 and R4 are unknown on the right side. That means T1, T2 are unknown in the first two equations, and R3 and R4 are unknowns in last two equations. So that we can calculate T1 and T2 first, we can rearrange the equation as given here. We write first two columns of the stiffness matrix multiplied by a vector containing T1 and T2 plus last two columns of the stiffness matrix multiplied by last two rows of the temperature vector, which is equal to the original force vector. We can rearrange the above equation and we can finally write first equations as this: a matrix containing 3 minus 3 minus 3 13 as members multiplied by a vector containing T1 and T2 equal to a vector containing minus 10 and 62.5 as members. In order to solve T1 and T2, we have to invert the matrix as shown and has to be multiplied by the vectors, and the final value of T1 and T2 will be equal to 1.917 and 5.25 degrees Celsius respectively. So the temperature vector theta is known now, that is theta equal to vector containing 1.917, 5.25, 10 and 10 as members. Once we have the temperature vector, we can calculate how the temperature of field be inside the two elements. Let's look at element number 1. Txy will be given as summation of shape function multiplied by nodal temperature. There are 3 nodes, so there will be 3 terms added together. As this expression uses the local node numbering, so we need to actually find out the local temperature vector, that is T1, T2 and T4. And we know that the first shape function is equal to area A1 divided by A. The second is equal to A2 divided by A for this element, and third is A3 divided by A for this element. We know that area of this element is 3. A1 is expressed in terms of determinant, so we put the values of x2, y2, x3, y3 here, and we get the value as 3 minus 1.5x. Similarly, A2 is equal to, we get 1.5x minus y, and A3 is again expressed in terms of determinant containing x1, y1, x2, y2, and the value is y. So temperature distribution Txy is given by shape function matrix multiplied by the temperature vector for that element, and flux distribution is given by Q, which is equal to minus small k multiplied by gradient of temperature function, where Txy is given above, which is temperature distribution, which is also equal to minus k B matrix multiplied by the temperature vector for this element, and B matrix we have calculated already. So Q will be equal to minus 4 multiplied by the B matrix, which is minus half, half, 0, 0, minus 1/3 and 1/3 as members, multiplied by temperature vector for element 1, which is vector containing 1.917, 5.25 and 10 as members. So Q we get equal to vector containing minus 6.667 and minus 6.333 as members, which is a constant matrix. Okay, for element number 2 also we need to compute the temperature and flux distribution. So we will do the similar process. The global temperature vector is given, and you see the global node numbering. Again, T is expressed in local node numbering only, so accordingly we have to extract the local temperatures from the global temperature vector. We get T equal to the shape function matrix for element number 2 multiplied by the temperature vector for element number 2, where the shape function 1 for element number 2 is given by A1 for element number 2 divided by area for element number 2. Similarly, N2 equal to A2 over A for element number 2, and similarly N3 equal to A3 over A for element number 2. Area for element number 2 is equal to 3 meter square, same as that of element number 1. A1 for element number 2 is calculated using a determinant equations. The value is 6 minus 1.5x minus y. A2 for element number 2 we calculate similar to element number 1, and we get A2 equal to 1.5x minus 3, and A3 for element number 2 also we get equal to y. So temperature distribution again given by Txy equal to shape function matrix for element 2 multiplied by the local temperature vector for element 2 And flux distribution again can be calculated. Q equal to minus small k gradient of T, and the final value becomes equal to minus 8 multiplied by a matrix containing minus half, half, 0, minus 1/3, 0, 1/3 multiplied by the element temperature vector, that is a vector containing 5.25, 10 and 10 as member. Note that gradient of T you can calculate directly by differentiating Txy with respect to x first and then with respect to y. The final value Q is equal to a vector containing minus 19 and minus 12.667. Note that this is a constant matrix. That really means that the flux distribution inside a three-noded triangular element is constant, while temperature is linear. The flux is constant. Now, in the next video, we will derive shape function as stiffness matrix for rectangular element for a 2D heat conduction problem. But I would like you to try it yourself first. Until then, bye.